All right, so for the grade 10 syllabus and for the assessment section, or what is going to be assessed for the grade 10 year of 2020 is question 8. Sorry about that, question 8. And question 8 deals with exothermic and endothermic reactions. It deals with our reactions as well as leads into the stoichiometry section. So without further ado, let's have a look at this question. 8.1 says that 8.78 grams of oxygen gas is required to react with an unknown mass of hydrogen gas to form water vapor. And a balanced chemical equation is shown. There it says oxygen gas O2 brackets G plus H2 gas gives us H2O, and we see the equation is balanced. We have balanced 2 in front of the hydrogen gas and a 2 in front of water. And the first question, 8.1.1, we know is a definition question. It asks us to please define what the term exothermic reaction is. So can anyone in the class define what an exothermic reaction is just off the top of their head? When a reaction is exothermic, okay, it involves, as I said, where heat is released, but the full definition, we know the exothermic reaction, okay, is a reaction where energy is released during a chemical change. So when a chemical change is occurring, okay, and we notice that heat is released, all right, in other words, heat is given off, such as a combustion reaction, okay? A combustion reaction, we know, involves oxygen, okay? And combustion is almost like a bit of onomatopoeia because there's always a loud bang or an explosion that happens, all right? So heat is always given off or heat is released when a combustion reaction, i.e. a reaction that involves oxygen, occurs, okay? So that's 8.1.1, which is an exothermic reaction. Any questions on that one? 8.1.2, they ask, is this reaction a synthesis or a decomposition reaction? And we need to state a reason for our answer. Now, if we think about this question, this is a type of question where we get in an exam where we might not understand what they mean by synthesis. But thankfully, we do understand what we mean or what they mean by decomposition. Because decomposition, we have seen that term more than once before. We know that involves the breaking down, all right, or disjoining, all right, but taking apart of compounds. We're not taking apart water here. We are actually creating water or forming water, or water is being formed. So it's definitely not a decomposition reaction. Therefore, it must be a synthesis reaction. So that's what we'll do. We'll state in 8.1.2 that, well, it can't be decomposition. So therefore, it must be synthesis because new compounds or a new compound are forming. Okay, new compounds are forming or a new compound is being formed. All right, or we can also state that reactants are reacting to form new products. Right, because that's the opposite to decomposition. Decomposition is when the product is being decomposed or broken down to form or to go back to reactants. Synthesis, meaning we are reacting two different elements together to form a new product or a completely new compound. 8.1.3, calculate the number of moles of water vapor that is formed. Water vapor meaning that is the gas phase of water, and as the reaction shows us, it is indeed in the gas phase. Okay, so for 8.1.3, all we do is we use our normal mole formula, which is the number of moles. What we can do first is we are given the mass of oxygen. The mass of O2 is 8.78 grams. Okay, this is stoichiometry. And we also know the molar mass of oxygen, or we can actually work out the molar mass of oxygen. We've got O2 there. That must be 16 times 2. That must give us 32 grams per mole. And this we can find on the periodic table. Okay? So now I want to work out the number of moles of oxygen first, because I have stuff to work it out with. So I got my formula, the mass over the molar mass of the substance. So I've got 8.78 divided by 32, and therefore the number of moles of oxygen must be equal to 0.273 moles. Okay? Now, our reaction was as follows. Oh, let me keep it white. Our reaction was as follows. We had O2 gas plus H2 gas. That gave us water vapor in the gas phase. And we had to balance our equation as follows. Okay? So we have a mole ratio of 1:2:2. And we need to calculate, obviously, water. Alright? To calculate water. So we got the number of moles of oxygen. And the number of moles, or the stoichiometric ratio for water is, or for oxygen to water, okay, is 1:2. So if 1 mole of oxygen, so this is how we can position ourselves, we write O2 is to water. Continue the ratio. We've got the stoichiometric ratio is to 2. And worked out the number of moles in this mole ratio, which was 0.273. Now, how do I get the number of moles of water according to the mole ratio, or what is known as the stoichiometric ratio? That's the real name for it. Okay, the stoichiometric ratio, which is this part over here, or what you see over here. We have to take this divided by itself, or the stoichiometric ratio of oxygen, because this is the number of moles. So 0.273 divided by this mole ratio, which is 1, times it by 2 to get it in terms of water. Alright, and if we do that, punch it on a calculator, because let's just take this times by 2 because it's divisible by 1. We get 0.546. So the number of moles of water is 0.546 in terms of the mole ratio. Alright? Or if you want to round it up to 2 decimal places, you can decide to say, well, okay, if that's the case, because remember, hydrogen is also in the same mole ratio as water, so you can say, well, number of moles of water, H2O, is equal to 0.546, or you can round it up to 0.55, and the number of moles of hydrogen gas will also be equal to the same thing, 0.546 or 0.55, whichever one you decided to round up or down, whichever one you decided to do. Okay, so that's how we work out the number of moles of water vapor, which was actually just this part over here. And don't forget to actually put mole at the end of that. So let me just put mole. All right. Question 8.2 says the reaction between zinc and dilute hydrochloric acid is represented by the equation below. Zinc is solid plus hydrochloric acid gives us zinc chloride and plus hydrogen. And the states of matter is put there. We've got zinc in solid, hydrochloric acid in aqueous solution. We've got zinc chloride in aqueous solution plus hydrogen, which is in gas, and it's a balanced equation. The concentration of hydrochloric acid solution is 0.1 mole per decimeter cube. The mass of zinc chloride formed is 0.85 grams. Define the term concentration in words. Okay, now your definitions are obviously important. So let's go define that quickly. 8.2.1 concentration. Okay, is the amount of a substance, very similar to the mole, but it has a bit of an extension, so it's amount of a substance that, or I would say that is present, but we can shorten it to say the amount of a substance present per volume of a solution. All right, so which obviously gives testament or backs up the formula, which is C is equal to N over V. The first part being the amount of a substance, which is the mole. That's what a mole is. The mole is an amount of a substance. And the last part, present per volume of a solution, which is the bottom part. So literally, if you just learnt this formula, C is equal to N over V, you would be able to form this definition over here by just looking at the formula. Okay, that was the definition for 8.2.1. 8.2.2 asks us, is the above reaction an example of a redox reaction? Write down yes or no and give a reason for your answer. I'll do this question, okay? Apparently they've amended redox out of your syllabus, so redox shouldn't be tested, but you know, anything can happen. So let's just learn it anyway, because I'm quite nervous about this revised edition, or revised ATP, because not everybody's going to stick to it exactly. Anyway, so if you look at that, is the above example of a redox reaction? So the answer is yes, it is. All right, and I'll explain why. Okay, is that because an electron transfer does take place between the reactants. Okay, an electron transfer does take place between all the reactants, or the charges of all the atoms in reactants and the products, they do change. Okay, and this comes back to oxidation numbers. If we must count the oxidation numbers across each of these, we'll find that they actually do change. So that's how you would have tested it, by going back to your knowledge of oxidation numbers. I don't encourage that just because it's not being tested that you forget it, but that you still remember it, because it still gets used a bit in grade 11, or can be used in grade 11. So I'm going to choose to write down this one, the charges of all atoms, in reactants and products changes. And then 8.2.3, which looks like it's the last question of question number 8. Okay. Question number 8 for 8.2.3 says, calculate the volume of hydrochloric acid that is needed to react with zinc to form 0.85 grams of zinc chloride. Okay, so this is a very important calculation. Okay, very important, because again we use mole ratios again. The first place that we need to start is always write down our reactions. So what I'm going to do is I'm just going to start on a new page. So we write down our reaction that was given to us. So we had, write it in white, zinc solid plus hydrochloric acid, which was in aqueous solution. And we had zinc chloride, which was in aqueous solution, plus H2 gas. And the only balancing number we had was a 2 there, over here. So now we look at our stoichiometric ratio. Our stoichiometric ratio suggests, okay, that we have a ratio of 1 for zinc is to 2 over here, and we have another ratio of 1 is to 1 for the product. So we have 1 is to 2 is to 1 is to 1. Okay, so because we are given the mass of zinc chloride, we can go ahead and determine the number of moles of zinc chloride. So pick another color. So number of moles of zinc chloride is equal to the mass of zinc chloride divided by its molar mass. And they said we had 0.85 grams divided by the molar mass of zinc plus Cl2, which we can find on the periodic table. Depending on which periodic table you are given with which molar mass values that you get there, some have decimals afterwards, some are rounded up to whole numbers, but you'd get a value of approximately 136,4, and you would have gotten a value of 0.0062 mole. So now that I know the moles of zinc chloride, okay, the question, going back to it, says calculate the volume of HCl. So I'm looking for the V of HCl that is needed to react with the zinc to form. All right, so this must react with this to form 0.85 grams of this. So you want to know what volume must that be. So I look at my mole ratio. So my mole ratio of HCl to zinc chloride, because HCl is what I need, is 2 is to 1. All right, so I've got HCl and I've got zinc chloride, and I have the mole ratio of 2 is to 1. And I worked out the number of moles for zinc chloride to be 0.0062 mole. So what do I need to do now? I need to find out the number of moles of HCl according to my stoichiometric ratio. I've got 2 is to 1, or if I read it from right to left, I've got 1 is to 2. Right, so I need to find out what is this number of moles in terms of the ratio. So I take what I have of the 1, which is 0.0062, divided by 1 times by 2. And therefore, the number of moles of HCl, according to the mole ratio, will be 0.0124 mole. It's just that times 2. I didn't even have to divide it by 1. Okay. What else? What other information did they give me at the start of the question? Because now, in my check sheet, I have the number of moles of HCl. I also have the concentration of HCl because they gave it to me in the question. They said the concentration of hydrochloric acid is 0.1. So now all I need is the volume of HCl. Therefore, C is equal to N over V. I substitute 0.1 in for the concentration, That's equal to the number of moles, which I just calculated. I'm going to divide that by volume, which is still unknown. I need to just rearrange my equation. Divide that now by 0.01. And I'll end up with the volume should be equal to 0.0124 divided by 0.1 should equal to 0.124 decimeters cubed. So what that's saying is I need, what that is saying is that 0.124 decimeters cubed of hydrochloric acid was needed to react with zinc, Zn solid, to form 0.85 grams of zinc chloride.